Basically, after talking about the sensors, we will talk about the following layer, which is the data coming from the sensors and the management of the data to prepare the data for applications development. Basically, just a little bit of a recall of the context of the project and why do we need to look at smart water management, etc. So everything now can be measured. We're in a very smart building where the quality of the air can be measured. The windows can open and close depending on the conditions here. The thermal comfort needs to be considered, as well as the usage of energy and water, etc. in the building. So this is due to the fact that everything is now becoming connected, and that on top of this we can create a decision support application that will help managers of buildings to take considerable or important decisions for saving energy, saving water, etc. So, and from there, lots of smart environments appear, like for managing energy, for managing traffic, and here for managing water. So all together we'll be all looking into how to use ICT for making our life better. Right. So the challenge that we'll be talking about in my presentation is basically, so we're talking about sensors and we're talking about applications. A wide range of applications can come up here, but the essential part, which is really required for good applications and to make use of these sensors, is to manage the data coming from these sensors. And that's a kind of a challenging issue. It's not really a simple thing because we need to look at different facets: how to collect the data, how to save it, how to aggregate it maybe, how to enrich the data, link it to other data sets, how to integrate multiple sources of data together into a place that we can easily query and make sense of it. So the main challenge is, or maybe the objective here, is to prepare the data for applications developers. So I'm not really targeting end users at homes, but I'm targeting end users in the project that develop the applications. Right, so just a quick overview of the architecture of the entire system. That's not a very complicated one here because it's the basic components of every smart application, or maybe smart concept somehow. So we start with sensors, we collect the data from the sensors, and then we build applications and services that use this data. So a quick overview of this layer. It was already, you had details about the leak detection sensor from Joanne. But the project looked at different types of sensors as well. There was the 3 different types were used effectively from the project. So there are existing ones that are installed in the pilots, but 3 main ones were experimented in the project. So some of them are the prototypes, like for example the leak detection sensor, the ultrasonic sensors from VTech as a partner in the project. So 43 sensors were installed in the different pilot sites. So these are a few pictures from the household installations in Thermi. This is one of the sensors installed here that we will show you during the tour of the building. And these sensors were installed in 3 of the pilots, of the total 4 pilots, because the 4th pilot had its own already sensors pre-installed, or maybe installed during the building. Right, that's a quick overview of the sensors. But the most important part for me and for this talk is the data space, the linked water data space. We had to think about, first of all, the sources of data that we're considering. It's not only sensors that are observing different types of appliances, including toilets, but I don't think that we have toilets. We're observing toilets in the project. But anyway, there are more important data that we need to consider is the building data, the shape of the building, how the network is used, or how the network is built within the building. Some enterprise data might be interesting, like for example school terms, non-school terms, if we're considering a data educational environment, and then other relevant open data. So there will be, like for example, the cost of water, CO2 emissions, maybe weather data could be relevant as well. So the thing here is that every piece of data is kind of separate. So every silo of data is kind of having its own contained in its own database or container. And the object of the first object, or the first challenge that we had to face, was how to break these silos and how to link together these different types of data. The solution is, we're coming from the research center that looks into semantic web and linked data, and that was a kind of jumping to the eyes, is the use of linked data. So basically the idea is every appliance or every component or every part of the building has its own URI, identifier, and then we can link these information together. So I'll give you just an example here. Say we have a kitchen that will have an identifier that will describe us, let's say that this is the main kitchen and that consumes 83 liters per day. In the kitchen, that's the relation contains, we can have appliances like here a dishwasher that consumes 40 liters per day. And maybe we have Mr. Coffee here as well that consumes some water, etc. So this kind of graph that will describe or give us semantic description of the environment where the sensors may be installed. So, and we were looking at the data formats and how to describe this information, etc. And we came up with a minimal vocabulary that describes the different different entities of the project. So we need to have a sensor that has an identifier, has a certain type of description, which has a location where it is installed, which is visible to some users. We don't want to expose the data to everyone. We have to think about some security and privacy issues, and it observes a certain outlet. So it might be observing a pipe, but the pipe is serving a water fountain for drinking water, or a dishwasher, or a shower, etc. So that helps us to make to interpret the data easily. After this, after describing the data, we explicitly represent all the entities for the different pilots, and we put them in a data catalog. We defined WCAN, which is an adaptation of CCAN as a data catalog. So CCAN is an open source project for cataloging data, for creating catalogs for open data portals, etc. So that's a single point for searching our data. That's very interesting and very important for end users, which are here again the developers. They need to know what data entities they are managing, etc. And the metadata is available through a standard API, so we can query this WCAN, and then we can get all the data from this catalog. So this is how the catalog looks like. So we have multiple sources of data, including open data, are also declared in the catalog. Like you see the number 4 there for us is the smart environments or the pilots of the project. Some other numbers like the entities, I think, and that's also the data sets, etc. So this is an example of listing of the NEB this building entities. So we have sensor M1, M2, M12, and well, there should be also further ones. But basically that describes the sensors, so ID, the type of description, the location, etc. So this information is highly required for us, like before we build our applications. Right, and then we were talking also about making the data available for others to query. So we put things in OpenCube. OpenCube is another project, open source project as well, that allows us to expose our data in linked data format. So users can, with some authorizations first, they can query the data using Sparkle. But we haven't really used this a lot in the project. We were mainly using WCAN as a primary data catalog. Then the other challenge now, after describing all the entities, is the collection of the actual data coming from sensors. So in this way, we looked at available architectures, and Lambda architecture was a deselected architecture because it allows at the same time to manage real-time data as well as historical data or batch data. So it has like 3 views, 3 interesting views, like when the data comes, either it will be considered as a real-time data or it goes to as a historical data. So basically real-time or historical, it depends on the frequency of the data management that you will consider. An adapted version of this architecture, which means a more complicated version of this architecture, is this one. So we have lots of external data that can be considered for as input for the platform. The first layer here, that's the entity layer. So here where we declare all the entities in the project. We might also extend that layer, but also talking about open data sources that we can declare in our data catalog. Then the layer in the middle is the batch layer. It's the historical data management part. So a pilot like this building, it's sending out data every day as a batch, so it contains all the readings of the day. So it doesn't make sense to go through a speed layer, which is maybe heavy compute one, but this one takes its time, it's fine. We can start this at midnight, and in the morning we can have the data available to query. The speed layer is collecting the data real time from the sensors. Whenever the sensor is sending us data to a particular message bus or middleware, then it gets processed and pushed to the data space or pushed to a database where it can be queried later on by the applications. Just a simplified version here. Say that we have a new data source that is coming to the data space. We first need to declare this in the catalog, and then we parse the raw data, we transform the data, and push it to the data store, where it can be either monitored by a dashboard, but it can be also enriched if it's need to be enriched with existing open data, and maybe mapped to other entities in the catalog. Right, this is also another version of the real-time now data processing. So say that we have a sensor. The sensor is sending HTTP requests to certain, using certain REST API to Kafka. This is our message bus. This is, think of it like an application that receives messages and direct them to the right jobs that are listening to it. So basically we have a Spark job here that continuously listens to what happens at this message bus, and then transforms the data and push it to the data store. In terms of technology choices for implementing the data space, we use Druid, Kafka, Spark. These are the shiny terms that are most of the time discussed when we're talking about big data, and they are made to be scalable for big data spaces, and they are kind of supported and used by big companies, big data companies. Right, so just to sum up here a little bit the data space. So for us, it was an experiment as well to experiment what Lambda architecture is, how to implement it, and see the challenges behind having actual implementation of this architecture. The use of semantic web, with no surprise, is something that we went for. Linked data as well. And then we have the two separate pipelines for ingesting real-time data, historical data, and we're using open data as well for enriching our sensor data. Some key benefits. So that becomes a one-stop shop for all the data. If an application developer joins the project and he wants to build an application, first thing he looks at is the data catalog. What data is available there? What entities do you have? How can I access the data, etc. It has the potential to include new data sources easily. So basically, new data source needs simply to be declared in the data catalog, and then the data from that source needs to be pushed to the query layer, or query mechanism needs to be associated to it. So that helps to reduce the integration cost, and that's called the pay-as-you-go data management approach, and that's basically using lots of standards and open data adoption. Some of the key impacts: it's a one data space for all the applications. You will see with Christos a wide range of applications developed within the project, that all of them, they first of all have to go through the data space. Then we adopted an open source strategy for the development of the data space that goes into the wave of European trends now in the adoption of open source, that because it helps to increase visibility of the project being developed within Europe for an international, let's say, dissemination. Training and education, we did a lot of trainings, and the most recent one is 2 weeks ago. I gave a lecture in the students in Master of Data Analytics, where we gave them the data from this building, 1 year data, where they were analyzing it, identifying any outliers in the data, any over consumptions or very low consumption, etc. And also the use of open data, because it's there is a huge push now to towards open governance, open data, and open data projects. Right, what will come next is basically the applications. Just to give a little flavor of what will happen, is basically making sense of this data means making the data look differently, making the data available to developers for either analyzing it, for detecting any potential savings, or maybe for detecting leakages, etc., etc. And maybe I'll repeat another slide that Owen put this morning. It's about some interesting numbers. More than 10 services and libraries were used. More than 20 applications were developed in the project. 20 data sets, I would say even more, because I haven't updated the slides since then. But definitely, I think we should have like at least 10 more data sets that we need to include here. And that's it. That concludes my presentation.